Yeah.
Or just once you see that you know how to do it, or you know, and you're not really gonna know what he's wanting until you get in there.
Yeah.
Stupid. You see this one. Just go 5 minutes. So I'll get your. Let me know. 3 hours. Oh.
Okay, we are starting the class. We have a lot to cover today. We talked about simple linear regression last class. So And we briefly talk about some basic concepts about machine learning. So under what circumstances we use regression, and what circumstances we use classification? When the target variable is what type of data we use in regression, and what type of data we use the classification. The target variable.
Regression when like use one category
For one
use like one category of data.
one category.
Yeah.
Yeah.
Like
Regression is for numerical data.
Yeah.
When the target variable is numerical data, we use that regression. And when the target variable, the data we want to predict is the categorical data, different types of watermelon, different types of houses, or different types. Then we use a classification. Okay. Basically, regression is y equals ax plus b, or y equals ax squared plus bx plus c. Or it could be a multiple regression with multiple variables. So today we are going to cover multiple regression and polynomial regression. We'll use this Boston data set from the library, and I just load this, copy this code and load it. Okay, good. First, let's get familiar with this data set. We can use, we defined it. We stored the data set in this variable data set. So we can use this method to get the basic information. Get the basic information of this data set. We see as the 506 rows, 506 instances, and it has 13 variables. They are either numeric or categorical. So we said linear regression is expressed using the formula y equals ax plus b. Right? Then how we deal with the categorical variable? If this variable is categorical, we cannot use this formula. So when we look at this variable here, river, whether it has a river crossing or not, then it uses the number 1 to mean the river crosses, and 0 means it doesn't cross. So if this affects the price, then it also has the weight ax or of bx3 or x4, this variable, right? So in linear regression, when you have a categorical variables, you have to transform them into numerical. Use 1 represent yes, and 0 represent no. So if it has this categorical variable has multiple options, then it will be transformed into multiple columns, and each column represents 1 value in this variable. So in your assignment, I included the instruction. With the instruction, you will be able to transform the variable. Okay. So, but that's a common way we transform categorical variable in regression model. Okay, other things looks fine. All other variables looks numerical. So we use this to call the data, and also for using the data set in the library, you also have to get the target variable separately. Okay. So so now we can transform it into data frame, so we can visualize it better, and also we need that to prepare for the linear regression model. The pandas data frame. And for the data, we give this data to the data frame. And then we give the columns. Okay, so we also need to give this a target variable to the data frame. So we can add a column to the data frame. This is data set dot target. Okay, now let's take a look at this new data frame. Okay. Right, everything looks correct. So next step is data cleaning. Usually we want to drop some columns that have too many variables, and we need to see how many null values it has. But in this data set, it doesn't have null values, and if I use this is now to calculate the null values, it will return 0. However, often in a lot of times, the null values are written as the zeros here, right? So you have to be careful of that. Even if it shows no null values, some columns may have too many zeros, and these columns are not useful. For example, here, if we check this ZN, 372 rows. We have a total of 500 rows, so could be a column can be removed. And the same with the other column, Charles. Yeah, this is even worse. The one I would definitely remove this one. But sometimes this is the column, it could be waterfront. Okay, only very a few of property have waterfront, but it doesn't affect the price significantly, and you want to keep it. So you need to check that, but you may not, you may decide to keep it or remove it. Okay, and that's definitely a necessary step to check whether the variable is important, should be kept or not. And also for one variable is that has too many null values, and also another type of variable you have to be careful of is the variable that has all the same type of value. So we call it no variance in the variable. So this variable all has a kind of a same value. Okay, it's not affecting the price of the target. Yeah, there's no difference in this variable, and that makes sense. John explain it. And yeah, it has all the same value, all similar value. Then you also could consider remove that. Okay, and still we have quite a lot of variables here, and common way to evaluate whether the variable is associated, is influencing price or not, is to use the correlation coefficient. So simply we get we use this method to get the correlation coefficient of each variable to other variables. And we can say it gives us a matrix of a correlation coefficient. So number one means that this is this correlation coefficient, it goes from -1 to 1. -1 means that it has a perfect negative correlation with the variable. 1 means that it has a perfect positive correlation with the other variable. For example, here 1 means that the same self, of course, they have the same value, and it has a perfect correlation with the self. And here, if we look at the price, this variable. So -0.3. When this number close to 0, then it means the weak correlation. And when it goes to -1, like the bottom one goes to -1, means that negative correlation with the variable. This one. So be careful. This the correlation coefficient. We learned the coefficient for the formula for the simple linear regression ax plus y. So when you get to the a for the x, it's also called a coefficient. So that is to express to explain how the x increases, how the y increases when the x increases when in the formula. Let's see. You call this a also coefficient, right? Slope or coefficient. So this coefficient is different from this correlation coefficient. Right? This one only means that whether it has a strong correlation with the variable or not. For example, here, if I draw a so this one, the correlation coefficient for this one might be close to 1 because it fits perfectly. It fits perfectly with the line. However, this one, the slope of this one is the same. The slope of this one is pretty the same with this one, but the correlation coefficient for this one is probably 0.8 or 0.7 because it doesn't fit the line perfectly. And I included the instruction here, how this is calculated, how this correlation coefficient is calculated. If you're interested, you can learn it. Okay, this is a good video, the best video I can find to explain how this correlation coefficient is calculated. So this is a concept we have to be careful of. Let's come back to the. Okay. So let's get this price. The last column is the last column is for the price. So I get the last column and sort the values. Okay. So the smallest number is -7 and the biggest number. So here, which values are has strong correlation with the price? Which variable? If you Rn, yes, it's close to 7. Well, which one? List, yes, list. Which one goes next after these two?
Are you talking about the ZN or the B? You're talking about the column B?
Column B, this one?
Yeah.
No,
Or did
So,
you say the one
what?
after RM?
no. As we said, this one goes first. This one is -7. So which one is the first that has the strongest correlation with the price? List, yes. And the next one is the RM. Which one goes the third? Yes, this one. As the -5. So -1, +1, they both have strong correlation with the price, but one is has a negative correlation, one is has positive correlation.
Oh, so like for the graph, the one is this way, the negative is this way.
Yes, so the negative will be so if the dots are like this will be negative.
Okay.
And it will be close to 1 because they pretty much line along this line.
Okay, and so the L stop one was closer because it's closer to -1 and the RM is close to 1, like further from the 0.
What did you say?
Like the L stop one,
Yes,
so that one was the closest correlated because it's closer to -1.
Yes,
And the
yes.
other one's close to 1.
yes, this one is close to 1, but this one is stronger because the 0.7.
Okay.
So we could use these variable to, we could use these variable as the x1, x2, and to build the linear regression model if we want to build a simple one. And also, what we like when we're building regression model, what we like to have a simple model that is explainable. You, after you're building the model, you want to explain this to your audience, to your boss, right? So if the model is better, it's simpler, it's better. Assuming that R value is good, R squared value is good, assuming the accuracy is good, then the simpler is better because that you can explain the data. You can explain what factors, what variables are affecting the price, and also we want to reduce the variables, the columns, because when the data is very big, more columns takes more time, takes more space to process the data, to create the model. So and there are more reasons that I think, but basically the most important reason is that less fewer variable, it takes less time, more efficient, and also makes the model easier to explain, more interpretable. Okay, so now we need to get those two columns, get these two variables, and then let's target. What we need to do next is to, since we have 500 instances, we can split this data into training data and testing data. So we only use the training data to build the model, and then we use the test data to test whether this model is a good one or not. Why we do that? Because when you build the model, it's built on the training data. It tries its best to find a good model. However, it may not fit for the testing data. So it's a common practice that you use the training data to train the model, and then the test data to evaluate the model. What we use is this library. This library, train, test, split, this method, right? And let me just copy this. So for this method, I need to give it it will split the it will split the xy. Y is the target variable, and x is independent variables, the extraordinary variables, the columns affecting the y, the target variable. And also you need to specify the test size, how many data you want to go into the testing data. Usually you 80% goes to the training data, and then 20% goes to the testing data. That's a common practice. And this random state is like the seed, or we mentioned the random method at the beginning of our class, right? You have to set the seeds, set a number to the seed. So every time you generate the random number, it will be the same. This random state, this parameter serves the same purpose. If you write 5, every time you split the data set, it will split the same. It randomly take out the testing data and the training data, right? So if you don't set up this number, every time it will randomly draw from the data set. But if you set up this number 5, they use the same method, and every time it split the data, the testing data stays the same. So it's repeatable. Your experiment will be repeatable. So X, so here we want to get the X. So Y is the, okay, I quit again. Let's, okay, I'm gonna this. So this is the X, this is the Y. Let's set up the Y first. Y, which one should be Y? Which data should be Y? Yeah. Y is the which one? Price, yes. So I just give it as the price. And I guess that's all we need to give it time. And the X is yes. Let's see if it's correct. I need the index. I believe that's correct. Usually you take it out and define an X. And then a variable Y. Okay. Testing. Let's run, see if it works. Okay. So let's see now what the training data look like. It looks the correct result, right? It has the two variable as the x. And you should also check. Usually, you should also check the shape of the data frame and to see if the shape is correct. All right, then with this new data set, I guess we can now go ahead to build the model. What did we use to get the linear regression package to the model from the package to build the model, just like the simple linear regression we did. We use the linear to get the model. Let's call this the model 2 or model 1. I need to get this method from the library. Obviously, I couldn't remember the library. So yes, so we get this from the library, and then we call this method, and then we train this model. And train this model is to use a fit, okay? Fit, and give it the x. The x is then now it's a x trained, right? X training. That's a x. We split it into training data set and testing data set, and the y should be a y training data. And I guess that's all we need to train the model. Okay, and then use this model. You can predict any number you want. As I said, I believe we mentioned the last time you need to give it a 2D array problem. Okay, perform the prediction. Yeah, you need to give it a 2D array for the data. So now with this model, we trained the model, and we can get the coefficient and the slope of this model, and to see what the line should look like. So okay, I return the intercept is this one, and the coefficients are these two numbers. So what should be the y-x relationship look like in a formula? Y equals the so this is x1. Okay, x1 means list, whatever you call this, and x2 is Rm, and then and then the intercept, right? So what should this formula look like? This is a -1 is the coefficient for which variable?
Yeah, also,
Yes.
This, yeah. So, and this one is the coefficient for Rn. So what does the formula should look like? Veronica? Just to give it to the coefficient to the, this is means slope, not coefficient, slope. Give this to the variable. It should be -1, -0.7 x1 plus 4.5 x2 and plus the intercept. That's the formula we got. Plus, that's the formula we got. We forgot to the last step. The last step is to evaluate the model, right, with the R score. So model 1 score. If I use the training data set, and see if I use the training data set, what will be the R score? We should use the testing data. Yeah, we could use the, this form only gives us the R square value of the model. You could use this for the training data, but you can also use it for the testing data. But since the model is built on the training data, we would expect the R square value for the training data is smaller or bigger than the, yeah, smaller, because the model is built on the training data. That looks there's something wrong. Obviously, this training data, this R score is 0.63, and this testing data, you get R score 0.66. That doesn't sound right. Must be something wrong here. Yeah, this model 1 uses the training data, so it must be bigger. When it's close to 1, it's better, right? The R square value, when it's close to 1, the model fits the regression line fits all the dots better. So I would expect that this is closer to 1, and this is smaller. Yeah, this is unexpected. Let me go back to the first time I run this to see. Pretty much the same.
What is the standard of score? What is the standard of score? R square or
what is-
how can they score the points? I mean, there is R square. Is that R square?
Yeah, R square. And R square is a relative value. It doesn't have, it's not affected by the number of dots it has. So, it should, this one, it should be higher for the training data and lower for the testing data, since the model is built on the training data. But it could be this testing data has a smaller size, so it has a it's data higher score. Maybe the testing data, those dots are closer to the line. That could be, but I cannot explain why this is a larger. Okay, let's move on. I may run some more data set and to see what comes up with the training data set and the testing data set. I would expect the R square value for the testing data set is usually larger, usually smaller. Okay. And then with this model, you can use the some new instances to predict the price. Next, we're going to talk about a polynomial regression. For example, with this data set. With this data set, okay, it kind of follows a straight line, but maybe goes a little bit curve and a curve polynomial equation makes it better. So let's see. If I build the regression model, I should use this to build the regression model and get the R score and see. In order to score. This is a good number. It's closer to 1. However, maybe we can find a number. We find a model that even fit it better, but a little bit curved. So we can try to build a polynomial regression model. How do we do that? We have to take some extra steps than this linear regression, because you cannot just call a method and then train the data to a polynomial regression model. Instead, you have to first transform this x, into x and x squared. So, and then use this linear regression model again. So basically, so we change this x, since we have a column x, and you can easily get all the numbers for x squared. So now we have x and y. So you can build use a method. We transform this x into x, and then a new column x squared, and then y. So now with the x squared, we can treat it like a linear regression. So you can do a y. So with these numbers, and then now you use the linear regression to build the polynomial model. You got the x, you calculated another, you build a new column based on the x. You can do simple math, right? And computer can do that for us very quick. And you get a new variable, a new column based on this x. That's x squared. And then with the y, so with the y, so and then you apply a linear regression to build this model ax plus b plus b and plus c, be a slope. So this comes the polynomial regression, right? So you cannot call a method directly. First, we have to transform this x into x and x squared. That's the method we use. Yeah, so we called this method polynomial features, and then we'll add a feature to that data set. Now we only have x where one variable x. So if we add features to the data set, and the second feature is the second feature we add to is what is the second feature we are adding to? X squared, yes. And then now we get a new data set, x poly, so what the x new. Okay, I just call it x new, and then use this method to get this new data set. I give it a variable here. I best this is all we need. And so this x new should be two columns. One is the x and one is the x squared. But actually it gives us three columns. So usually it gets not just x squared, x and x the zero, what we call x zero. Okay, that gives us the three columns. So the first one is the x the zero power, and then the x, and then the x squared. So now with this data we can build the linear regression, right? Let's say it's a linear regression. You could use this one, then you couldn't, but you don't have to. This is all one. So even if you use a linear regression model, the linear regression model will return this as a no correlation with the y. All has a one, only has one, number one. So the same. Now we build the model. So the x should be this new data, right? This new x. And the y is still the same. It didn't change anything. And let's see the score. I call the status model 3. Okay, it did give us a higher R square value. Looks this model does fit in better. Let's see what's the new equation. The new formula should look like. So this is the intercept and the coefficient that returns us. This is the intercept and that's the coefficient 0 and 2.22 and then negative 0.2. So what should be the equation look like now? Y
or 0 multiply x1. 0 multiply first column x1.
Well, x and the x square. So what is the 1 for
2.2.
2.2? Yes, the point is for the
Negative
uh-huh.
0.2.
Yes, and then the -2, right? And then the intercept. The intercept here, -1. (1.2). Okay. Do we have any questions so far? No. Then we can plot this regression line on the. We can plot this regression line on the scatter plot. Using this data, you can plot this regression line. Let's try to plot this regression line. We do use a scatter plot is to plot the x and y, and then you draw another line plot. Line plot, the x and the y should be the predicted number, right? Like the y number on the model should be the predicted number. So it should be the model 3 predict x. No, you cannot give it x because this model is built on the built on the new group with the x square. So you should use the new group new array with the x square as the variable, as the values, input values for the model. So this should be x new. That's the input for our model 3, right? That's the input for our model 3. So with this prediction, you should also give it these variables. And I use a color. And I'll compare it to the first model, the simple linear regression model we used, X, and model 2. This model 2, it's a simple linear regression used. Let's give it X. Okay. So I'll give that the both models. This is the simple linear regression, and this is the polynomial regression model we built. So can we use a higher degree, like a X cube? Or that model fits the dots even better?
Right.
Uh,
Right.
yeah. Now this is the R squared, and this is the 2 degree polynomial regression model. So can we build a model with a 3 degree, third degree X cube and X squared? Will that model fit better for these dots? Yes, it will. So theoretically, you can build a model with any degree, and when the degree is higher, this transforms more and will fit the dots even better. That's degree 2 degree gives you 1 hump, and then 3 degree gives you 1 hump, and then 1 line. And 4 degree gives you 2 humps. So the higher the degree is, the more freedom the model has to fit all the dots. However, it comes a problem. Well, these fit even though these fit the training data set, can build a very good model. For example, here. I'll do that. And I get some training data, okay? And then I have some testing data here also. If I use a higher degree model to fit all these training lines. Okay. Well, this model fit for the testing data. Well, this model fit for the testing data. No, it doesn't fit for the testing data. These still have a long distance to the regression model. However, if I use a lower degree model, actually, the distance of these testing data to the regression model is smaller than the higher degree model I just used. So this is what the concept of bias and variance. Bias, so when we build the model, this model cannot fit perfectly to the dot as a distance to the, it cannot fit perfect to the dot. It has distance to the training data. Now, if this line, if this line fits perfectly with the data, we call it a lower bias. If it doesn't fit perfectly with the data, for example here, maybe we have one more. No. You have more data here. Then it's called higher bias. Okay, the better it fits the training data, the lower bias it has. And also, we have another concept called variance to measure, to explain whether the data, whether the regression model fits the training data, the testing data or not. So if it fit all the testing data, we call it a high variance. High variance. If it doesn't fit the data, I believe this is the testing point. This is the low variance. So if it accommodates the testing data, adjusting to more points, the testing data is called a low variance. And if it doesn't adjust to the testing data, see this line has a long distance to the testing data, are called a high variance. Right. So usually we want to find the prediction model with a low bias and a low variance. However, oftentimes when you have a low bias, that means that it has a high variance to the testing data. So it's a trade-off. You want to find the best points. You want to find the best points that has both lower bias and lower variance. And what we call total error. We use this total error to find the best model with the low bias and low variance. It cannot go perfectly low. That's a high degree model. It doesn't accommodate the testing data. So this is a concept about the bias and variance and the bias variance trade-off. And also we often say overfitting when effort fit perfectly, try to fit perfectly to the training data. It's called overfitting. Overfitting, if fits perfectly, and try its best to fit the training data, but it's not a good model. And also it's a concept called underfitting. So even it's really scattered, you couldn't even build a model. You build a model on it, and then it's called underfitting. It really doesn't fit the dots and has a high bias. This one is underfitting, and this one is overfitting. Okay, not overfitting. Okay, believe that's all the concept we want to cover today. So next week we'll start we'll start another model for classification. Okay. Any questions? for today. Yes.
So earlier when we transformed the X, we were trying to see which degree polynomial will make the model like predict better.
Yes, we did that, yeah, and we see the second degree, the polynomial model fits better for, but, real situations that you don't use the polynomial model very often, it's not explainable. Unless the data clearly shows that it's a curve, then you use it. It depends on what data do you got. So if the data really shows that it's a curved polynomial shape, a curved shape, then you could try to use that model. And usually you use the simple linear regression model more often. And when you use use the model for multiple variables, this this polynomial regression will make the model very complicated, hard to explain. I think when you're using the models, it's really important to you follow the data